So let's use some of the properties of logarithms to solve some problems. So sometimes they'll give you a certain logarithm. Say they know log base 3 of 5 is approximately equal to 1.4650. You're going to use this known information and what you know about logarithms to solve logs you don't know, like say log base 3 of 45. So we can use our properties of logarithms to rewrite this in a way where we have a log base 3 of 5 we can put in and hopefully know all of the other parts of it. So here I can rewrite this as log base 3 of 9 times 5. And I want that 5 in there because I know log base 3 of 5. And I can use my product property of logarithms, and I can say that's the same as 2 logs added together. So log base 3 of 9, which is just 3 squared, so I just rewrote that 9 as 3 squared, plus log base 3 of 5. This I already know. I know the approximate value here. Right here, I'm going to use the power property of logarithms, move that 2 up in front. So I have 2 times log base 3 of 3 plus, and I just substituted my approximate value in for log base 3 of 5 right here. Now log base 3 of 3 is equal to 1. 3 to what power equals 3? Anytime these match, whatever that is, it's going to be to the first power. So this is just 1 here. So I have 2 times 1, which is just 2, plus 1.4650. And I should probably have some wavy lines here. I just add those numbers together and I have 3.4650. So that's my approximate answer to this problem. And you can always check to see if it makes sense. 3 to what power is going to give you 45? So you can think about your powers of 3. 3 to the third power is going to be 27. 3 to the fourth power is 81. So 45 is in between those two. So you expect the answer to this to be somewhere in between 3 and 4, and it is 3.4650, and that's approximate. So then we can go ahead and take a look at this. And remember, we want to write it in terms of log base 3 of 5 or log base 3 of 3 because we know that's 1. So here we can rewrite 125 as 5 cubed. So this is the same as log base 3 of 5 cubed. And then we can take that power by the power property of logarithms and bring it out in front and multiply. So 3 times log base 3 of 5. We know what this is. It's given right here. So it's equal to 3 times this approximate value, which gives me 4.395. And this is approximate too, so those should probably be wavy lines. Now there's lots of different ways you can do it. You can break it up. I'm just going to give you an example of 2 ways we can do this bottom one. So we have log base 3 of 25. I could either write that as log base 3 of 5 times 5, and probably that should be in parentheses right there. But then I can take that 5 times 5 and I can break it up into 2 different logs and add them. So log base 3 of 5 plus log base 3 of 5. I know what that is, so I take those, I add them together, and it's approximately 2.9300. So then over here, instead of writing this as a multiplication, I can write it, as to a power. So I have log base 3 of 5 squared. And so then I can take that power, pull it out in front, and I have 2 times the log base 3 of 5, which is just this, which if you notice, it's just 2 times this over here, and I get the same answer. So as long as you're using the properties of logarithms correctly, you can do it lots of different ways. So let's take a look at a little more complicated example where we're asked to solve using those properties. So we wonder what x is going to be. We know what this side of the equation is. That's just some number, and it equals the log base 3 of x. Now, when you have unknowns in logarithms, there are 2 ways you could do it. This is kind of the first way. If you have logs on both sides and they have the same base, you can get everything all together as 1 log on this side and 1 log on this side, and then compare what you're taking the log of because of the property of equality of logarithms. So that's how we're going to solve this one. There's another way you can do it, and we'll do the next problem like that. So right here, I'm going to rewrite this as 6 to a power. So I have my number out in front, and I can use the power property to just make that be an exponent. So log base 3 of 6 squared, just making that be an exponent instead of pulling it out in front, minus log base 3 of 16 to the 1/4. Again, just making that be an exponent, and I didn't change anything on this side. So then I can go ahead and calculate this. 6 squared is 36. 16 to the 1/4 power. I'm taking the 4th root. So I want to know what times what times what times what gives me 16. It's 2. So I have a 2 right here, and that's equal to log base 3 of x. I didn't change this at all. Now the other way you could do this is you could turn this into a negative exponent and make that be a plus. But then this part would be a little bit different. So, but you would get the same answer. So here I'm going to use the quotient property of logarithms. I have a minus sign, I have 2 logs. I can combine those into 1 log, and I can make it be a division problem. So this is the same as log base 3 of 36 divided by 2. Notice I've gone from 2 logarithms to 1 logarithm here, which was my goal. And then I can simplify the 36 over 2 to 18. And I have log base 3 of 18 equals log base 3 of x. So by the property of equality of logarithms, if the log of this is equal to the log of this, these two things must be the same, and I can say 18 is equal to x. And that's the property of log equality. So if I took 18 and put it in here, and I did this, all of this calculation, I would find that x is going to be equal to 18, and these two sides of the equation are equal. So let's look at the other way when you have an unknown in a logarithm. So here you'll notice I don't have logs on both sides. So a couple ways I could do this is I could turn this into a log. I could say that's log base 10 of 10 and then solve it the same way I did the other problem. But the other way I can do this is if I have it equal to a number, I can rewrite it in exponential form. So let's take a look at how this works. Here I have a plus in between there. I have 2 logs and they're both base 10. If there's nothing written, remember they're just base 10. So I can rewrite that as a multiplication problem with 1 log. So I'm taking 2 logs, making it into 1 log, this is base 10, of z times z plus 3. And that's still equal to 1. That's the product property of logs. And then I just wrote this 10 down here because it'll make converting to exponential form just a little bit easier. So I just wrote the 10. It's a common logarithm, so I know that that's a 10. And then rewriting in exponential form, I have 10 to the first power is equal to z times z plus 3. And then I'm going to go ahead and distribute the z's. I'm trying to solve for z here. You've probably seen a problem like this before. So I distributed, and it's a quadratic. Anytime it's a quadratic, I set it equal to 0, just in case I can factor it and use the 0 product property. So I have z squared plus 3z. I'm going to subtract a 10 from both sides so I can set it equal to 0. I go ahead and factor it. I have a z plus 5 times a z minus 2. So then setting that equal to 0, z plus 5 equals 0, z would have to be negative 5, and z would be positive 2. Now, here's the tricky part. If you remember the graph of the logarithm, you can't take the log of a negative number. It doesn't exist on that. It gets closer and closer to that 0, but you can't take the log of a negative number. So you have to look for those solutions. So in this case, z equals negative 5 is not a solution, and only z is equal to 2 is your solution. So you have to discount that negative solution. And you do have to go back and see if when you plug it in, you are actually taking the log of a negative number. For example, if this one right here was z squared, and I'm checking to see if it would be a negative number, if I squared negative 5, it would be a positive number, and then that would be okay. Not in this one, but in this one. So you want to take it back and make sure you're not taking the log of a negative number.